Hello, science fans! Today, let's dive into a topic that affects every single one of us: energy. It powers our lives in ways we often take for granted, but the choices we make about how we generate it have huge consequences for our planet and our future. Every day, we rely on electricity for everything, from lighting our homes and keeping our food fresh, to charging our phones, running our hospitals, and even streaming our favorite shows. Our modern world simply can't function without a steady supply of power. Traditionally, we've powered our world by burning fossil fuels like coal and gas. While these sources have fueled incredible progress, they also release massive amounts of carbon dioxide and other greenhouse gases which drive climate change and pollute the air we breathe. To protect our planet and ensure a healthier future, we need cleaner energy sources. That's where nuclear power comes in, a technology that's been around for decades but is often misunderstood. Unlike fossil fuels, nuclear plants don't burn anything. Instead, they split atoms in a process called fission, releasing huge amounts of energy without emitting carbon dioxide. This makes nuclear one of the cleanest large-scale energy sources available today. A single nuclear plant can provide steady, reliable electricity around the clock, rain or shine. It doesn't depend on the weather, making it a powerful backbone for our energy grid. But if nuclear is so clean and reliable, why isn't it everywhere? Why do some countries embrace it while others hesitate? The answer, in a word, is fear. Specifically, fear of meltdowns and the potential dangers of radiation. Traditional reactors use water to cool their cores, but if that cooling system fails, the core can overheat, leading to a meltdown and the possible release of radioactive material into the environment. Disasters like Chernobyl in 1986 and Fukushima in 2011 have left deep scars on the public imagination, making people wary of nuclear power's risks. These reactors depend on complex safety systems, pumps, generators, and human intervention to keep everything running smoothly and safely. If those systems fail, catastrophe can follow. The consequences can be severe, both for people and the environment. This fear has held nuclear power back, despite its enormous potential to provide clean, reliable energy on a large scale. But what if we could make nuclear power truly safe? What if new technologies could eliminate the risks that have haunted the industry for decades? That's the challenge and the incredible opportunity at the heart of our clean energy conundrum. The future of our planet may depend on how we solve it. Imagine a world where nuclear power is not only powerful but also completely meltdown-proof. What if the fear of catastrophic nuclear accidents could be a thing of the past? That's exactly what China's top scientists and engineers are striving to achieve right now. They're pushing the boundaries of nuclear technology, determined to make this vision a reality for the future of energy. At the heart of their efforts is a revolutionary new type of reactor, the Integral Fast Reactor, or IFR. This isn't just an upgrade, it's a complete rethinking of how nuclear power can work. Unlike traditional nuclear reactors, IFRs are designed to be walk-away safe. Even if there's a total power failure, these reactors won't overheat or melt down. Their safety systems work passively without human intervention or electricity. China is leading the world by investing heavily in commercial-scale IFRs, moving beyond theory and small experiments to real-world, working power plants. These advanced reactors use fast neutrons and a unique liquid metal coolant, typically sodium, instead of the water used in most reactors. Fast neutrons allow the reactor to extract much more energy from the same amount of nuclear fuel, making the process dramatically more efficient and reducing the need for fresh uranium. Liquid sodium, unlike water, can absorb and transfer heat at much higher temperatures, which not only boosts efficiency but also adds an extra layer of safety to the system. One of the most groundbreaking features of IFRs is their ability to recycle nuclear waste. They can use spent fuel from older reactors as a new energy source, turning a dangerous byproduct into valuable fuel. This means far less radioactive waste to store for thousands of years, and much more energy squeezed from the same resources, making nuclear power cleaner and more sustainable. If China's approach succeeds, it could completely transform the global nuclear industry, making nuclear power safer, more efficient, and truly sustainable for generations to come. These new plants are both power generators and recycling centers, working together to close the nuclear fuel cycle. If adopted worldwide, this could mark a major turning point for global energy, helping to power cities while protecting the planet. Let's break down the science behind IFRs, or integral fast reactors. and see what makes them so different from the nuclear reactors we're used to. Traditional nuclear reactors rely on slow-moving neutrons to split atoms, but this process only taps into a tiny fraction of the energy stored in uranium fuel, less than 1% in fact. IFRs, on the other hand, use fast neutrons. Imagine the difference between a gentle tap and a powerful swing. Fast neutrons are like that powerful swing, able to break apart more types of heavy atoms. These fast neutrons can split not just uranium-235, but also uranium-238, which actually makes up over 99% of natural uranium found on Earth. When uranium-238 absorbs a fast neutron, it transforms into plutonium, a new fuel that can be used to generate even more energy, creating a self-sustaining cycle. Thanks to this process, IFRs can extract over 99% of the energy from uranium, compared to the mere 1% used by traditional reactors. This means we can get far more power from the same amount of fuel. With this technology, our existing uranium supplies could last for thousands or even tens of thousands of years, making nuclear energy much more sustainable. Another key innovation is the use of liquid sodium as a coolant. Unlike water, sodium doesn't slow down neutrons, allowing them to stay fast and keep the chain reaction going efficiently. While water cools traditional reactors, it also slows neutrons, limiting efficiency. Sodium, on the other hand, keeps neutrons fast and cools the reactor core extremely well. Sodium's excellent heat transfer and its ability to avoid slowing down neutrons are crucial for both the efficiency and safety of IFRs, helping to prevent overheating and allowing for stable operation. Because sodium operates at low pressure, there's no need for the high-pressure systems or complex pumps found in older reactors, reducing the risk of accidents. The result is a reactor that produces more energy, generates far less waste, and is inherently safer than traditional designs. IFRs represent a major leap forward in nuclear technology, offering a cleaner, more efficient, and more sustainable way to power our world. Designed for both high performance and peace of mind, IFRs could be the future of safe, reliable nuclear energy. Nuclear waste has always been a major challenge. Traditional reactors leave behind highly radioactive spent fuel that stays dangerous for millennia. Fast reactors like IFRs change the game. They're nuclear waste recyclers. Spent fuel from old reactors, once considered waste, becomes valuable fuel in IFRs. These reactors burn up long-lived radioactive elements, turning them into electricity. The byproducts are still radioactive, but their danger fades in hundreds, not hundreds of thousands of years. This dramatically reduces both the volume and hazard of nuclear waste. Existing stockpiles of spent fuel become a resource, not a burden. With IFRs, we can power our world for centuries using yesterday's waste. It's a sustainable, closed fuel cycle, once just a dream, now within reach. The real breakthrough? Passive safety. Traditional reactors need pumps and power to keep cool. If those fail, disaster can strike. IFRs use passive cooling, relying on physics, not machinery. The reactor core and heat exchangers sit in a giant pool of liquid sodium, which acts as a massive heat sink. If the system shuts down, sodium naturally absorbs heat for hours or days, no boiling, no meltdown. Hot sodium rises, transfers heat to a secondary loop and cools as it circulates, no pumps required. This natural convection keeps the core safe, even in a total blackout. The reactor is designed to fail safe. It cools itself automatically. No human intervention needed. This is what walk-away safe means. Even if everyone leaves, the reactor stays cool. Passive safety could finally earn nuclear power the public's trust. It's a new standard for reactor safety. The risk of meltdown is engineered out. This isn't just theory. China is building these reactors now. The flagship is the CFR-600, a 600-megawatt sodium-cooled fast reactor in Fujian province. Connected to the grid in 2023, it's already generating clean electricity. CFR-600 is a commercial-scale prototype, testing and perfecting the technology for future reactors. Its success proves large-scale fast reactors are viable. Next up, the CFR-1000, a 1,000-megawatt reactor set to begin construction by 2028. China's plan is to deploy a fleet of these reactors, creating a closed fuel cycle with existing plants. The goals solve nuclear waste, boost fuel efficiency, and provide massive clean power. China is building the future of energy, one reactor at a time. These projects show advanced nuclear can fight climate change and power the world. The future is arriving now. Let's sum up the impact. First, IFRs extract nearly 100 times more energy from uranium, turning a finite resource into a near-limitless one. Second, they slash nuclear waste, transforming a millennia-long problem into a manageable centuries-long one. Third, they can recycle old waste, cleaning up decades of spent fuel. Most importantly, passive safety means no meltdowns. Public fears can finally be addressed. These benefits could also lower costs over time: more energy per fuel, less waste to manage, and simpler safety systems. Standardized designs and mass production could make clean nuclear power affordable. Safe, clean, abundant, and cost-effective energy is within reach. IFRs could transform the world's energy landscape. They offer a real solution to climate change and energy security. The promise is huge, and closer than ever. Of course, challenges remain. Sodium coolant is reactive with water and air, so reactors need robust containment and safety systems. China's designs use multiple barriers and inert gas to prevent accidents. An intermediate sodium loop keeps radioactive material away from water. Advanced sensors detect leaks early, allowing safe shutdowns. Reprocessing spent fuel is complex and must be done safely in shielded facilities. China is investing in these capabilities, but strict oversight is essential. There are also concerns about nuclear proliferation, since fast reactors can produce plutonium. However, the plutonium is mixed with other radioactive elements, making it hard to use for weapons, and international safeguards are in place. With careful engineering and regulation, these challenges can be managed. What does this mean for our future? Meltdown-proof waste recycling reactors could be a game-changer in the fight against climate change. We need clean, reliable power. Nuclear can provide it 24/7. China's leadership could inspire a global shift to advanced nuclear energy. As more reactors are built, costs will drop and technology will improve. This could launch a new era of safe, sustainable nuclear power. Imagine abundant, clean energy powering our homes, cars, and industries without warming the planet. We could clean up old nuclear waste and move beyond fossil fuels. Advanced reactors offer energy independence and environmental protection. They can help developing nations grow without increasing carbon emissions. The challenges are real, but so is our capacity for innovation. By embracing science and bold ideas, we can solve the energy paradox. The future of energy is here, and it's awesome.